The key to mastering a subject does not solely rely on your mathematical proficiency or the inherent complexities of the topic. Rather, it hinges on your ability to make informed choices and select an appropriate learning approach. Learning a subject effectively is less about your innate ability and more about strategic decision making regarding learning platforms, selecting the right book, and making the right choice. By making thoughtful choices and aligning them with suitable learning patterns, you can significantly enhance your comprehension and mastery of any given subject. In this video, you are going to learn about 7 important steps which will make differential geometry easy for you. Not only you will learn the subject, but you will also get to know which book to read, how to start the subject, how to overcome difficulties, and where to fetch those resources. My name is Shaunak and you're watching this video on my channel, Physics for Students. Welcome to this fresh video on mastering differential geometry, a very easy and a 7-step approach which will give you the success. Now, because differential geometry and this video is related about selecting the right path and selecting the right approach, I would like to first start with this very picture where there are 2 roads which are diverging in the wood, and I would like to quote few lines from the famous Robert Frost's poem. 2 roads diverged in a wood, and sorry I could not travel both, and be one traveller long I stood, and looked down one as far as I could to where it bent in the undergrowth. Now, Robert Frost took a different path in this poem, but the question is that what path or what approach will we take so that we get to the right target and master differential geometry? Which road would we take in this wood, that is differential geometry, whether we will take the left hand side road or the right hand side road? That is basically the central idea of today's video. Before we go ahead and understand all those things, first here is a very quick understanding for those who are quite new or willing to learn is what is differential geometry, coming up into the next part of our video. Now, if I take the basic definition, you can see that differential geometry is basically a kind of a mathematical discipline which generally studies about the smooth shapes and smooth spaces, and which are known as smooth manifolds. We will come to this topic, what do we mean by smooth and what is not smooth. But first of all, let us understand that there are 2 words which are involved in this understanding. First is what is called differential, and second one is called geometry. So when we talk about differential, we are trying to make an understanding that we need to learn calculus. Second, obviously we are using differential and integral calculus to make things easy, and we would be studying the subject of surfaces and manifolds technically, where we would be using calculus or differential or integral calculus as a whole. Also very important for all of us to know is that differential geometry is a subject which is very local. That means it deals with the periphery or the geometry of surfaces, which is very local and absolutely which is not very global in nature. We come to the next word, which is geometry. That means it will deal with the geometric properties. We will start with the Euclidean properties, which gets extended to non-Euclidean part, and that is where the differential geometry comes into, and it is also something which helps to study with the sizes and shapes of these objects. So differential geometry is basically about using calculus, differential, integral method, and studying some local properties, geometrical properties from Euclidean, which gets extended into non-Euclidean. So here is a comprehensive definition. So in essence, differential geometry reflects to the core idea of using differential calculus to study and analyze geometric properties of smooth shapes and spaces. Why we are calling smooth, why we are not calling it not a smooth, we will come to that part later. So this gives you an understanding about the subject, what differential geometry is all about. Now, before we go ahead and start to pick up the path where we will go into the Robert Frost's wood, whether we go to the left hand side or right hand side path of the jungle, there are few things which we need to check, or rather few of the things I would say as a prerequisite that you need to check. What are those things? Let us look into this part of the video. What are the things that you need to check? The first thing is that definitely differential geometry relies heavily on the concepts of differential as well as integral calculus. So it is a kind request to all of you, those who are studying differential geometry or planning to study differential geometry, should have an absolute mastery or should have a very good idea about differential calculus, because the entire concept of calculus will be used, explored, exploited on either way in the subject of differential geometry. Also, as you see, the word itself is geometry, so it heavily relies on the concepts of Euclidean geometry, obviously, which gets extended further into non-Euclidean geometry. And lastly, the most important thing is that this is the first time probably when from undergraduate to grad, or the mathematics course that you are taking, you need to be very aware about a lot of proof-based mathematical system. Why? Because in differential geometry there are a lot of theorems which needs to be proved. Just in the case of Euclidean geometry or our school lives, when we are doing the Euclidean geometry, we used to make mathematics to prove those theorems. Here also it is going to have the same thing, but on a much more rigorous mathematical way. So if you have not you're not aware about what is a proof based mathematical system, how to make a proof, I would request please go back and you need to look into those things. So a heavy mastery of differential and integral calculus, a good understanding of the Euclidean geometry, and understanding of what is called a proof based mathematical system, because there are a lot of proofs which needs to be done in differential geometry. So to summarize all things, if we talk that what is the mathematical prerequisite of what are the things that you need to do, not much. Yes, you need to have a very good understanding of calculus. You need to get the basics of linear algebra very good. Here I have cited real analysis, assuming that you have already taken a course in real analysis. Otherwise you can understand what is called a proof-based mathematics system, and you need to understand what is called Euclidean geometry. Now the first, second, and I would say the fourth one you already know, but this one I have highlighted in red because until and unless you know real analysis or any kind of a proof-based mathematical system, it will be difficult for you to learn differential geometry, because you cannot just plug and play the formula to make use of that. Rather, you have to do a lot of proofs which are going to be very important. Just in case of real analysis, which gives you the pleasure, or you can see the birth of different theorems and concepts of calculus. Here also in differential geometry you will see a lot of things which are just like a newborn baby which are born, but you need to have an understanding of what is called a proof-based mathematics. So you need to have an idea on that. Now, having said that, what is differential geometry? What would be the mathematical and conceptual idea that you need to know before you go into differential geometry? You might be wondering that why should I learn differential geometry? Is it that it is just to get my good grades in mathematics, etc.? No, there is definitely a broader aspect in order to learn differential geometry that we will look up next. In this section we are going to learn that why you should learn differential geometry, coming up next into this part of the video. So when we talk already that we have learned that what are the mathematics that is required, you will be surprised to know that when you're learning differential geometry, it is not that you're learning the differential geometry part much better, but you will see that you're learning your calculus much better, because there are a lot of tricks, tips, and I would say minute subtle details which are actually used in differential geometry, and you might have to revisit your concepts of calculus. So what happens when you start learning a thing which is right in front of you, you again go back to your earlier lessons and then you brush up and get things better. So this is also the case that you will learn calculus much better. Also, you will see that there are a lot of fundamental concepts, I mean to say, in terms of geometry, space, matter, manifolds, surfaces, shapes and sizes, which evolves in learning differential geometry. So yes, the fundamental concepts are better. You will also develop a greater power for problem solving, because I told that there are a lot of proofs which needs to be done. deepens your understanding of space. In this part, space, what do I mean by that? The shapes and sizes, how things from Euclidean geometry gets into non-Euclidean geometry, how the basic proofs of elements, Euclid's elements really do not work. So the concept of space gets more extended, complex, and much more enhanced. So that is very important. You see that there is a connection. This is an interdisciplinary, I would say, advantage in learning differential geometry, is that it connects not only the pure mathematics part, it also connects physics, engineering, robotics, computer graphics, because the differential geometry is such wide that it actually connects to a lot of areas. So if you learn one part of the differential geometry, you can easily migrate, or you have a better knowledge in the other parts of the discipline. If I talk the application part of differential geometry, obviously the first thing is that general theory of relativity is heavily dependent on differential geometry, where you learn things better. Robotics uses differential geometry. Nowadays computers also use. AI and data science is heavily dependent on differential geometry, and a part of genetic engineering, which I have cited in my earlier videos, where the genes are actually counted on the Riemannian manifold, is being used or depends on differential geometry, and many such things. So this gives you an idea that it is not only for the career part, but for your mental enhancement, improving your problem solving abilities, and in a way that you can get connected to a lot of interdisciplinary ideas other than pure mathematics. Differential geometry is the key for you. Now we understand that we are doing this, or we are trying to learn differential geometry and other areas because it's a little bit complex. Now what are the, basically I would say, the problems in learning differential geometry? I won't say problem, I would say that is a kind of a challenge. Let us look into those part of the in the next part of the video. Why I'm talking about problems? The reason is that once we understand the problems, then we can find out a possible diagnosis to this problem. So the first thing I would say that rather the challenge in differential geometry is that there are a huge amount of books available. Which book you should start with? Why you should read this book? What is the method, or how will you study, and what is the process and method for study? So all these taken together, the basic idea which comes into your mind is that it is called a choice overload. Now, more choices are there, you find it difficult in order to learn any subject. Not only differential geometry, same goes with general relativity, quantum mechanics, complex analysis, various things. So if you get too much of choices, too much of books, too much of blogs, too much of YouTube videos, you really get confused and you really don't know which book to read, what is the approach and how to do that. So this choice overload is something which creates a problem within the students, and that is the purpose of the video, that how will we select the right book and come to a comprehensive result. So I would like to show you that when we talk about the problems in differential geometry, the basic idea is that you understand why you are studying the subject. That is the question mark, that do you understand it? Second is that you get a proper direction and objective when you learn this subject. Either ways, you start seeing what is in front of you. Same with pure mathematics and real analysis. I have seen that students really come to me and say that I really don't have a direction. I am doing maths, I'm doing sums, I'm doing problems, but I really do not have anything in front of me to see. So abstract mathematics starts to become concrete when you get a proper directive and a goal. You can also understand the practical application, which I showed you that other than the pure mathematics, there are so many interdisciplinary areas which you can focus on. And when you do the mathematics, if you get an objective, then you know what is the reason you're doing that. So I would say that you start loving differential geometry rather than just following the methods discussed in the classrooms by the professors. It is not a pure chalk and talk kind of a method, but something very much applicable and something which you can really see right in front, unfolding with a proper reason to go for. So this is basically what could be the challenges. Now that we have understood, we would first take the step. What is the first step to learn differential geometry? What are the books that you need to do? So I would suggest that when you're taking the first step in learning differential geometry, in order to go directly to the problem, I would suggest you to understand how differential geometry actually evolved from the concept of Euclidean and it got extended to non-Euclidean geometry. The first book I would like to show you regarding knowing a little bit about your past, because if you don't know about your past, you won't be able to understand the present, and forget about the future. That becomes more weird. So the first book that I would say is this one, Euclidean and Non-Euclidean Geometry by Mervyn J. Greenberg. Now hold on, in this entire video I will be talking about a number of books, and I would also say how to get hold of those books. So I would just like to show you, these are the different editions which are available. So if you get hold of any of this hard copy or soft copy or anything, should not be confused, because this is the first, second, third and fourth edition, and it contains around 665 pages. Yes, that is quite obvious, because the book traces back how differential geometry actually evolved from Euclidean geometry. So in Amazon it is quite high priced, I mean to say, as you can see the INR price, but I would give you a quick solution to get this book. And here you can see that this is the price which is currently available. And if you talk of Amazon, then you see these are basically I would say the different prices of this edition. So just thought to show you what are the different prices of this edition in terms of US dollar and INR. This is actually, you can see the rating is around 66% has been given 5-star, and this is the author Mervyn J. Greenberg, and he received his doctorate. I don't know whether you have heard about Sir Lang, is another famous differential geometry author in 1959 from Princeton University. Now if I go now to the what we call the reviews or the feedback of this book, it is absolutely wonderful. So here you can see whether for class or for personal learning, it is somebody saying remarkable, it was a good deal, exactly as described. So just to give you an idea, that is really a very good book to start reading. Now again, the question is that every book is designed or maintained in order to make a certain I would say certain part of the people educated. So that is why I want to show you that who should read this book. I mean to say, has the author shown that this is directed to a particular group? Let us look into the next part of our video. So here you see Mervyn J. Greenberg says that it is very prospective high school and college geometry teachers are presented with a rigorous treatment of the foundations of Euclidean geometry and an introduction to hyperbolic geometry. General education liberal arts students are introduced to the history and philosophical implications of the discovery of non-Euclidean. That means definitely it is made for those who are learning differential geometry, but those who are not into education, not into mathematics, I mean to say general education, people who are from arts, they can also learn it, because it gives you a complete and comprehensive idea about the history and how non-Euclidean geometry came into being. Here also you can see that Professor Greenberg has shown that if students do not do a good number of exercises, they will have following difficulty in the following subsequent chapters. So that means there are quite a good number of exercises in this book which you should follow. We come to what we called is the content part of the book. Although the book is quite extensive, I will just go and give you a quick glimpse of how the book is being organized. As you can see, the first chapter starts with the very basic Euclid's geometry, the Pythagoreans, the axiomatic method, the parallel postulates, and so on. A very brief survey of the beginnings of geometry, how the Pythagorean idea developed, the Euclid of Alexandria. So you can say that is the historical development of the book. It then goes into what we called the Euclid's first 4 postulates, an attempt to prove the parallel postulate. These are nice diagrams, quite well clearly sketched on the book, so that you really don't face any problem. The next chapter comes with what is called logic and incidence geometry, where theorems and proofs are being designed, as you can see that if then, and the entire logical, I would say, development when we use logic in geometry, otherwise how this has been organized. There are also examples of Hilbert's axioms, I would say the flaws in Euclid's elements, then the axiom of betweenness, what is the betweenness axiom, and so on. It also speaks about neutral geometry. The discovery of non-Euclidean geometry starts from chapter number 6, where we get the elements, where we get the accounts of Janus Boolay, Gauss, Lobachevsky, and so on. And this is actually a nice diagram, as you can see, how it evolves from Gauss to Riemann and further to Galois. what we see is that the geometric transformation, how it took place, I mean to say in terms of Felix Klein's famous Langle program, motions and similarities, and these translations, half terms, ideal points, and so on. Finally, the book culminates into discussing the, I would say, results in real hyperbolic geometry. It talks about Sacheri and Lambert's quadrilaterals, Boileau's construction in the hyperbolic geometry, and so on. So this is overall, this is just a glimpse. It is a very detailed book, and once you, as I was telling, that once you understand the past, then you can really appreciate the present, and you can very well go into the future. So this is overall the development of non-Euclidean geometry, how it started from Euclidean geometry. However, there are two more books. I mean to say, these are my favorite books. I would like to give you a very short glimpse, which also explains about the development of non-Euclidean geometry. The first book is called Worlds Out of Nothing, and it has got a very good Amazon rating of 60%, and it is by the famous historian, I would say, Jeremy Gray. I think you are all aware about this person. Professor Jeremy Gray is basically is an mathematician, but he more or less writes books on the history of development of mathematics. He has also got great books on complex analysis, how it developed, and so on. The next book is by Megan I. Dillon, and it is called Geometry Through History, and this is what the qualification tells about. He got his PhD in mathematics from the University of Virginia, and so on. So this is also a good book by Springer, which talks about the geometry, development of geometry through history. If you want, you can go ahead with that. Now, once we have understood that we understood the past, what is the development, etc. Now it is the time that we should take a deep dive into understanding few of these fundamental concepts, and that is step number 2. Some of the very fundamental concepts of differential geometry. I'm not going to teach and talk about the mathematics. What are those? There is a reason, because based on that, now I will be showing you what are the next books that you need to take. Obviously, the first one which comes is the curvature. So I've just given you a basic idea of what is a curvature. So the Gaussian curvature of a surface is a measure on how much the surface is in both an x and y directions at that point. The curvature of a surface, you can think it as the amount by which it bends or curves in 2 dimensions. Further, it can be taken. So curvature, the fundamental concept is that you need to have a good understanding of what is a curvature. That is step number 2. Step number 1, sorry. Step number 2 would be what is called a manifold. And I will show you there are very good literature and easy understanding of the concept of manifold. So what is a manifold? Very simple. Any surface that looks like an ordinary flat space when you zoom it enough. So here you can see this is, although it looks like a curved surface, but when you zoom it, it becomes absolutely flat. There are different ways in which you can perceive a manifold. What is a manifold? What is not a manifold? So the key idea is that even though the entire object is curved, small enough regions would be looking like a flat surface. So when you zoom a torus, say for example this one, this would look like a flat surface. So how do we define it mathematically? We call it a manifold is defined as a space that is locally homeomorphic to a Euclidean space. This means that for any point in the manifold, you can find a small neighborhood around that point which can be smoothly transformed into a flat Euclidean space without making any folds and creases. So point number 2 or concept number 2 would be very much important, what is called a manifold. The third point, which is called tangent spaces, or later it has been extended as tangent bundles. So the set of tangent vectors, remember it is a set, right? It is associated with set of tangent vectors associated with the point P of a manifold together with the operation for addition and multiplication is called the tangent space at P. So here you can see that this has just kissed the surface point, so that is why it is called the tangent and further to tangent spaces. So the tangent space at a point on a curved surface is a mathematical concept that what does it approximate? That the local behavior of the surface near that point. So concept number 3, you need to have a very good understanding of what is called the tangent spaces. The fourth point is that we all know about vectors. Now when these vectors are single, they are got a magnitude, direction, etc. But when it comes as a force or as a bundle, it is all called vector fields. So vector fields assigns a vector to each point on a manifold. So you can just think about a wind and you imagine a field where each arrow represents the strength and direction of the wind in a specific location. So vector fields are very, very important because it is used to describe the motions in space and in different areas of physics and engineering. The fifth concept, which is very central and there are a lot of important discussions, are called geodesics. Obviously, it comes very relevant to Einstein's general relativity. It means the shortest path between 2 points, right? And you can just imagine you want to go from one point to other on the sphere. What is the shortest route that you take? And the shortest route is not a straight line on a flat surface, but a curved path. So geodesics will have a lot of mathematics, proof, geodesic equation, how things happen. So geodesic is another very important concept which you should understand in order to learn differential geometry. The sixth and I would say a little bit advanced topic is what is called the Riemannian metric, and it defines the notion of distance and angle on a manifold. I'm not going too much into that because Riemannian metric, then I have to talk about Riemannian manifold. But Riemannian metric is a very fundamental concept, and it plays a crucial role in defining the geometry of manifold, which includes curvature, geodesics, and importantly volume elements. And manipulating and working with metrics can be algebraically complex, and understanding the geometric implications of different metric properties would require a visualization and intuition. So you need to have an understanding of Riemannian metric. The last and the most important, a little bit advanced concept is what is called a differential form. And you can just think that differential form is basically nothing but a coordinate independent framework, because we are moving out into generalization. We do not want to make ourselves restricted to any coordinate for expressing geometric quantities on manifolds. So differential forms becomes very important to study the behavior of quantities that change as you move through space. So a differential form, we can say, is basically a generalization of the concept of a derivative. So having said all those 7 things, the basic idea and objective is to make you understand that these are the central 7 concepts which you should have in order to start learning differential geometry. And the first thing, if you remember, when I started talking about some fundamental concept, was what is called learning curves and surfaces. And now it is the right time that you take the third step and select the perfect book to make you understand about curves and surfaces. My first, I would say, one of the best book would be this one, Marco Abbat and Francesca Tovena's Curves and Surfaces. I've just given 2 photographs of these authors. So this is a very comprehensive and a very step-by-step understanding of the concept of curves and surfaces, because without this we won't be able to understand. This is the book, and you see what the 2 authors write is that we do not require you to have exposed to algebraic topology. That means this book assumes that you really don't need to have an idea about algebraic topology. Now, what happens in various books which I have read in differential geometry, they do assume that you know topology, general topology, point set topology, but that again will take you some time to learn topology and come back. So I would always request you to select a book which assumes that there is no understanding of topology. So here you see the author has clearly written that what this section 2.1 contains a complete introduction to the theory of the degree of continuous maps and circles itself. That means there is no requirement to know what is called what you call the algebraic topology. So I am not going to discuss much about this book, which you can very easily learn. The second book will be P.M.H. Wilson's Curved Spaces. This is Professor Pelham Wilson, and it has got a 84% rating in Amazon as a 5-star. Although this book is wonderful, I've just given you a few glimpses about the content of the book. As you see, it starts again with Euclidean geometry, then moves into spherical, then triangulations and Euler number, hyperbolic geometry, smooth embedding curves, and so on. The third book, which is again a very good book, you see I'm only talking about curves and surfaces right now because this is a very central concept. This book, which is by Thomas Bancroft and Stephen Lovett, and here you can see that these are the photographs of these 2 authors. This is also a very good book containing a lot of proofs, etc. Here also you see that the author has written, we shall not prove these assertions, as a proper discussion of simple connectedness would take us too far into the realm of topology. And that is the reason that I have actually shown and I have underlined it. That means this is also a book which assumes that you really don't need to learn anything about topology. Further, as you see, the authors say that the reader should feel free to either skip the technical details of the proofs in the rest of the section, so and so. That means it is quite easy for you. You can just skip those things, and this skipping would not create any problem or any kind of disturbance in your learning. So these three books, which you can again rewind and play the video. The first one, which is starting with Francisco Abad. The second one, which is starting the second book, and the third one is by Thomas Bancroft and Stephen Lovelet, would be a wonderful book to start and making the concept of curves and surfaces absolutely great. So once we have taken this third step, I would say the second and the third step about learning the fundamental concepts and learning curves and surfaces, here is the fourth step, which I actually told you that after these curves and surfaces, what is the second step? It is called learning manifold. Now, in order to learn manifold, I would like to speak a little bit about how you should start learning manifold in the fourth step coming into the next part of our video. If you talk of the concept as a whole, what is manifold? So it again comprises, just like differential plus geometry makes differential geometry, many plus fold makes manifold. So many is actually coming from the West Saxon and Middle English word, which is many or manigi or managaz, which actually means many. And fold is coming from feld or field or Dutch woud, which means it is a kind of a crease. We will soon see that. So it actually tells that there is something numerous different elements having many features and forms, and fold actually means to wrap up or furl or bend or ply into anything. So we can say that manifolds are actually topological space or objects which deals with numerous and many shapes and form that are bent, sometimes furled or wrapped, with one part lying on another. And that is essentially the essence of Euclidean geometry, non-Euclidean geometry, isn't it? That we will deal with surfaces which are not very regular but which are fold. And so we can say that every point on a manifold which looks similarly that of a Euclidean. And we have seen that what is the term. Now when we are starting to learn manifold, we have to be aware about two concepts which most of the students miss or which is not considered to be important, because manifold will contain of two things. One is called a smooth manifold and one is called a differential manifold. There are texts, there are YouTube videos, there are books and lectures on both two, but the question is that which one you should first start with. So let us understand that smooth manifold is a special kind of a manifold that is not only topologically like Euclidean place but also allow for smooth functions. I hope I don't need to explain what is a smooth function, you can understand. Now differential manifold is similar, it is just like a smooth manifold but is a little bit more flexible. Why? Because it allows also differentiable functions, which means that you can take at least one derivative. So smooth functions are those that are infinitely differentiable. That means you can take the first, second, third derivative and so on. And in case of a differential manifold, you can take at least one derivative. That means that the manifold might have some kinks or sharp turns, which smooth manifold definitely doesn't have got. So this gives you a hint that obviously you should start first with smooth manifold, because you can apply, use multiple derivatives and it has got no sharp turns or kinks, etc. So smooth manifold, you can think the surface of a sphere which equipped with a smooth surface, and differential manifold is that of a cube because it has got sharp turns and kinks. So when you start reading a text or when you start reading the concept of manifold very deeply, you should first start with the concept of a smooth manifold. Here is what we call I would say a kind of an tabular structure to understand the difference between smooth and manifold. A smooth manifold is a special type of differential manifold where all function must be smooth. That means, which means they are infinitely differentiable. But differential manifold allows for functions that are differentiable. Smooth manifolds are more restrictive because they require a higher level of smoothness. Differential manifolds obviously are more general and versatile in nature. It can have a sharp turn, it can be smooth, etc. In a smooth manifold, the transition functions between overlapping charts, this is technical, I would not speak about that. So when one chart is overlapping on the other, must be infinitely differentiable. But in case of a differential manifold, the transitions functions between overlapping charts must be differentiable. So this brings us to a nice conclusion that all smooth manifolds are definitely differentiable, but not all differential manifolds are smooth. So here is an easy understanding. Smooth manifolds are the most well-behaved, and that is why we first start with the well-behaved part, allowing for smooth functions without any kinks or corners or rough turns. Differential manifolds obviously are very good because they are more general in nature with some degree of roughness. So it is all about the level of smoothness and differentiability you want to work with on your physical models. So which one to start first? I will myself show you certain points and you will get the answer yourself. On a smooth manifold, we can define calculate derivatives. On a differential manifold, it is not put. These concepts can become very difficult. Smooth manifolds are like sphere, torus, Euclidean space. Differential manifold are Mobius, real projective plane, etc. Application is mostly in physics, engineering, and application is in topology and differential geometry. Obviously, smooth manifolds are very easy to learn, and differential manifold, because they are generic, are more difficult and complex to understand. So this gives you not only the understanding of a smooth and differential manifold, also you get an answer from within you that yes, we should start with our learning smooth manifold. So first thing is that here now you see that the calculus concepts are easy to define, and differential geometry concepts also easy. And differential manifolds that are not smooth can be more difficult to visualize. And here also you will see that smooth manifold has got a lot of textbooks, online resources, etc. And differential manifold have got less amount of textbooks, online resources, and a very small community of mathematicians also whom you can interact and discuss about your problems of differential manifold. So what is the fifth step that we would take? The fifth step is that which is the first book or which is the best book to learn manifold, and your manifold, I mean to say, obviously it's the smooth manifold. So the first book I would say would be Loring W2TU's An Introduction to Manifolds. Amazing. 88% has given a 5-star, and you can see he is basically Taiwanese American mathematician, and he attended the McGill University and Princeton University, completed PhD at Harvard, and his doctoral advisor is none other than the famous Philip A. Griffiths. So having said that, you can see this is basically an overview of the book. So again, it starts with Euclidean spaces, smooth functions, and then it covers vector fields. You can see how these vector fields are nicely drawn on that. Then it goes into exterior algebra, multivectors, tensor product, wedge product. Then it comes to differential form on Rn. So it is quite a, I would say, a step-by-step understanding of the book. It covers chapter 2, which are manifolds, and you can see the photograph of the great Bernhard Riemann, and it goes into topological manifold, smooth maps on a manifold, and this is what I was talking, that how things overlap, the charts, etc. So this book has got quite a lot of good diagrams, easy explanation, and a lot of things like that. Diffeomorphism, a very important subject, explain examples of smooth maps, inverse function theorem, and a lot of other things. So these books also talk, as you can see, the content about manifolds, and these are smooth manifolds, quotient topology. Then it takes into tangent space, and it contains a lot of areas into tangent space. Then the Lie group and Lie algebras are also being covered. And I come to the next book. This is I mean to say Loring W2's book, which is, on my opinion, it is a very well arranged book and very well designed. The book clears the concept which you are required to do before learning manifold. This point number 2 is very important. Why it is important? Because some people or some students might not know the prerequisites. So the book does quite a good amount of justification to make you learn and understand the subject, and then the equations and things are very cleared up. And also I missed this part, is that it is one of the best book, and you can start learning smooth manifolds with this book. The next book would be the famous John M. Lee's Introduction to Smooth Manifold. Although it has got a 78% rating of 5-star, but still I think that it is, I mean to say, a landmark book. This is the photograph of Professor John, known as Jack Marshall Lee, American mathematician professor at the University of Washington, specializing in differential geometry. So this book of Introduction to Differential Geometry, again a few note which the author has cleared. It is for the first year graduate text on manifold theory for students who already have a solid acquaintance with general topology, the fundamental group and covering space, etc. The book is similar in philosophy and scope to the first volume of Spivak's classic text. That we all know what is Spivak's series of books on differential geometry. So yes, it actually gives you that scope. That means it is quite wide. Now here you see the author says that I try to keep the approach as concrete as possible with pictures and intuitive discussions of how one should think geometrically about the abstract concept, but without shying away from the powerful tools that modern mathematics has to offer. That means in order to visualize this abstract concept, how do you visualize them geometrically? So Professor Lee talks about that, and also not geometrically. He assures to the reader that this also concerns the powerful mathematical tools which are required. So I mean to say, you can see I'm just giving a kind of a glimpse of that book because it's quite a detailed book. You can go ahead and check it. Start with all those things like tensors, algebra of tensor, covariant tensors, and the Riemann distant functions. Then it goes into differential forms. It talks about the symplectic function, differential forms, and everything. Now, apart from reading the books, what I also feel is that very important for all of us to know is there are a good amount of lectures on Smooth Manifold. I mean, it's lectures which you can go to the websites and see. These are, I would say, these are very good. I would like to show you few of the lectures, and I have given those links to these lectures in the description box. First is the University of Notre Dame. The lecture, it is quite recent, November 9, 2022, and it is by Liviu Nicolasiu. I'm sorry if I'm making a wrong pronunciation of the French terms. So this is very good lectures on geometry of manifolds. You can go ahead and read it. It is on the website of University of Notre Dame, and it's a very authentic, as you understand, it's a university's website. I have cited this, I would say, lecture in the description box. Here is a brief idea about what are the lectures, what are the content. So again, it starts with manifolds, natural construction of manifolds, and so on. You can see it is quite extensive. It contains cohomology, classical integral geometry, elliptic equations on manifolds, and so on. The second one would be a very famous MIT open courseware, Geometry of Manifolds. You can go to MIT's website, although I have given it in the description box, and you can see there's a huge amount of topics starting from manifolds, derivative, more examples, stratified spaces, fiber bundles, and you can see all of them contains an icon PDF. That means these are all free, downloadable, and you can very well go ahead and see those lectures of MIT OpenCourse. It's good in terms of understanding manifolds. The third one would be from the University of Radboud University. Those who have watched my podcast, Alicia Castro, who was doing a research in quantum gravity, is from the Radboud University. I've given this also. So here you can see that manifold lecture notes, and it contains quite a lot of details about the manifold lecture notes and so on. So this would give you a very constructive and a very comprehensive idea on learning smooth manifold. I have cited lectures as well as books. The reason is that this is the foundation. This is the cornerstone of differential geometry. Without that, it will become very difficult. Now, having gone through the fourth, fifth, sixth, and so many steps, we come to the final step, and we need to pick up the right book of differential geometry. I mean to say, which textbook, which will contain everything starting from manifolds to curves and surfaces, differential forms, everything. Let us look into the next part of the video, which textbooks you will read in differential geometry. I will cite you not one, a little bit more books. The first has always been my favorite, Andrew Priestley's Elementary Differential Geometry. So if you are really studying alone, I mean to say a standalone course, this is one of the clearest and most accessible texts. No difficult proofs are given in order to make things really very complex. It's a very step-by-step approach. So Andrew Priestley's Elementary Differential Geometry would be my first recommendation. Again, a note, you see the writer has written, for readers unfamiliar with points of topology, this means so and so. So it is quite clear that in case that you really don't know points of topology, it won't create much of a problem. So it is a very self-complete one single book which will give you an understanding. Again, here proving global results about curves often requires concept of topology. Since we are assuming that readers of this book have extensive familiarity with topological ideas of this book, we will not be able to give complete proof. So the knowledge of topology won't again be required. And this is quite a glimpse of what it contains. It again starts from curves and how much does a curve, global properties of curve, examples of surfaces, curvatures of surfaces, and so on. The second book which I would like to recommend you is Christian Bach's Elementary Differential Geometry. Although the rating is not good enough, but I have read it personally. It is quite a good book. He's a German mathematician and mainly doing researches in differential geometry and mathematical physics. Now this book also starts with the very basics, just like Andrew Priestley. It is more or less the same, and here you can see the beautiful picture of M.C. Escher's. So actually it shows hyperbolic geometry, so it starts with curve theory, classical surface theory, and so on. It also covers a lot about what you call geometry and analysis. Not a very heavy book, around 300 pages, good one to start with. So it is written clearly and contains some beautifully colored graphics in the middle of the book. The last and a very, I would say, influential author, Barrett O'Neill, Elementary Differential Geometry, is also highly recommended. So he is was an American mathematician and is known for his immense contribution in terms of differential geometry. This is also, I would say, a very good book to start with. You can see that again there is a note, knowledge of elementary calculus and linear algebra. That means you just need to know elementary calculus and linear algebra. The reader will, for example, frequently be called upon to use the chain rule for differentiation, which we have learned in our school days. The book Elementary Differential Geometry, as you can see, these are the basic contents. So all the books are starting with the very basics, and that is the good news for all of you, that you really don't need to go into the advanced part right at the word go, but you can just go through the books and understand the very basics. So here is my honest opinion. This is a book clearly for I would say start your journey in differential geometry. Perfect introduction to the field, very concise but not too terse, and very well organized. I would say good content of the subject, and this is actually a very good introduction for differential geometry. Most importantly, all the books including this book has got a lot of exercises. These are quite good exercises, nothing to make life more difficult, and you can do it for self-study and so on. Now, having taken all those 7 steps, which actually frames up the entire understanding of differential geometry, the next most important things which starts is that how do you get those books? Because these books are quite expensive. What are the links and how to download them? Now, you see that on the proper, being a very proper, I would say, academician and a teacher from my side, I have given this book on the description box, which is there, and you can download this book. The second book, Introduction to Manifolds, is also there. An Introduction to Smooth Manifolds, John M. Lee, is also there. Elementary Differential Geometry link is also there, and Barrett O'Neill's book is also there. So, and not only these books, also I have given the links for the open courseware which is provided in the description box. If you're really wondering that apart from those things, how do you come across, how do you know or gather those books which I have already spoke a lot in this video, then I would request you that you have my WhatsApp number, you have my email ID, you can connect me, and I would look into your profile and I will try to help as much as I can in terms of providing those books to you. However, these 1, 2, 3, 4, 5 books along with the open courseware is provided in the description box. You can go ahead and download them very easily from the proper, I would say, clear link websites which are provided. So that's all for today's video, giving you an understanding 7-step approach to differential geometry. If you have liked the video, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. As I was talking about, this is my email ID where you can contact me, and this is my another channel which I put only and only on general theory of relativity. You can also follow me on my Facebook, LinkedIn and Instagram pages. That's all for today's video, and I hope that you will be enjoying all those 7 approaches which will make things easy, and the flow and the journey of differential geometry will be very smooth. Physics for Students will be again back with few more videos on different subjects, but till then, goodbye, and may the good Lord be with you.